this lecture, we will introduce a particular way of classifying batteries, and following that, we will elaborate on one kind of batteries. Much of this material is from these two references. So here we are classifying the battery in terms of its capacity to be recharged. So primary batteries are those that cannot be recharged. So probably a common primary battery are so-called alkaline batteries. You might have used it at some point of your life. They're rather common. However, they cannot be recharged. So you use it and dispose it off. As opposed to these batteries, the secondary batteries are those which can be recharged. Again, the two most common secondary batteries are the lithium ion battery or the lead acid battery. I'm sure you would have been exposed to lithium ion battery. It's there in your cell phones and so on. And lead acid battery are also a prevalent kind of class of batteries. So typically, a primary battery has a greater specific energy, that is the total amount of energy that can be obtained from a battery per unit mass is greater in terms of primary battery. It also has greater specific power, that is the amount of power that can be obtained from the battery per unit mass, that is also higher. Okay, so there are reasons for this, why a primary battery has greater specific energy and specific power compared to a secondary battery. We will go into this aspect later in the course. However, just to mention, give you a quick idea of why that is so, is that when a battery operates, there are structural changes in the electrode. Okay. So the greater loosely put, the greater the structural changes, the greater would be the specific energy and specific power. However, for it to be recharged, these structural changes should be reversible. If the structural changes are greater, you may get greater specific energy and specific power. However, you cannot recharge or reverse these uh, structural changes. Okay, so that's why um, primary batteries have these two um, good features. However, they do not have the feature of it being rechargeable. Um, Primary batteries and secondary batteries are so called because primary batteries were found earlier than the secondary batteries. Okay, so when when you look at the chronology, it's important to understand the time scale, which is one of the aspects I would try to stress in this lecture. So batteries are not new. The first uh, battery was demonstrated by Volta, as you can see, in 1800. Okay, so it's been there for a long time. So this is a real Volta pile from a museum. Okay, so what does this indicate? Okay, so this is the real Volta pile. Okay, so these are pairs of electrodes. One is a zinc electrode, another is a copper electrode, and separated by an electrolyte. Okay, so this may also be porous solid in which the porosity is needed for soaking up electrolyte. Okay, so these are pairs of um, electrodes. Okay, that's what a pile is. Okay, so typically when you say a battery, it contains many cell. Okay, so typically when you say a cell may refer to a pair of electrode, that is one anode and one cathode. However, a battery indicates many such cells put together. Okay, okay, so this is a schematic of a Volta pi. So this Wikipedia link elaborates on its history and how some more details of the Volta pipe. So this was in 1800s. So Daniel cell, which was a significant improvement compared to a Volta pile, was demonstrated in 1836. So as you can see, it took close to 40 years to go from a Volta pile to a Daniel cell. So what are the reactions in a Daniel cell? So the Daniel cell has a cathode, as I mentioned in the previous lecture. There are two ways of labeling the electrode. Either you can label them as a cathode or an anode, or you can label them as a positive electrode or negative electrode. So anode is where you have oxidation. So in the case of a primary battery, it's very clear. We can use this terminology of anode and cathode because these batteries are not rechargeable. Only one kind of reaction occurs in a particular electrode electrolyte interface. So at the anode, there is oxidation, and at the cathode, there is reduction. But the convention in electrochemical reactions is to indicate the reduction reaction. Okay, so always when we specify the electrochemical potential, we are always referring to uh, the electrochemical reduction reaction. Therefore, even in an anode, we specify uh, the reaction in the reduction form. Okay, so cathode, this is the reaction that is occurring. There is copper 2 plus in the electrolyte, takes up 2 electrons from the electrode and gets reduced to form a copper solid. Okay, so here it's copper 2 plus in the aqueous form, and this deposition is in the solid form. So at the anode, what is happening is the zinc metal, which is in the solid form, um, gives rise to zinc 2 plus, which goes into the electrolyte. And the 2 electrons are given to the wire. So the direction of the electronic current is in this direction. The conventional current is in the opposite direction. And in addition, there is the anion sulfate also are transported across the electrolyte. So there is a separator in some form or the other. It can be a porous separator, which is permeable to a particular kind of ions. Okay, so that's a common theme in many of these batteries. Um, so that's what is happening, and the role of a separator is to keep the two chambers, that is the electrolyte in contact with the anode, separated from the electrolyte that is in contact with the cathode. Okay, so you don't want them mixing together. Okay, so that's one of the role of this separator. So the first widespread commercialization of the battery occurred in 1868. Again, I want you to notice was in 1836. The commercialization occurred in 1868. Okay, so this is called a Leclanche cell. The main difference between that is you still have zinc. However, instead of copper, you have a different oxidizer. Okay, so MnO2 is the oxidizer. That is, it oxidizer is a component of the battery which itself gets reduced, but it supplies oxygen. Okay, so that's one way of thinking about it. And typically, in chemistry, when you talk about a reduction agent and an oxidizing agent is the component which gets reduced while supplying oxygen, and so on. Okay, reducing agent is reduces something else, but while doing so, it gets oxidized. Okay, so um, so the, so why do we, so the metal oxide we are talking about is MnO2. That is the positive electrode. Um, why do we need carbon? Okay, so you may see carbon often enough because most of these metal oxides do not have sufficient electronic conductivity. Just to re-stress, we do not want much potential drop anywhere in the battery. Uh, the potential drop here is because of um, insignificant or less than optimal electronic conductivity. To overcome that feature, you add a component which is a good electronic conductor. So the role of carbon here is to increase the electronic conductivity of the metal oxide. Um, so this being a metal, it is fairly good electronic conductor. It shows greater electronic conductivity compared to a metal oxide. So you do not really use carbon. So you may see carbon often enough in many of the battery system. One of its primary role is to increase the electronic conductivity. So again, at the negative electrode, zinc gets oxidized to zinc 2 plus, and at the positive electrode, MnO2 gets reduced to this particular compound. Okay. Um, Again, one thing to notice is that this is still an aqueous battery. That is, this is mostly water with some supporting electrolyte. So this commercialization occurred in 1868. So having water is not a very good option for the electrolyte. Okay, so you don't want um, some particular component of a battery to be sloshing around. So one of the goal was to replace water with something else. Okay, so that happened with the introduction of so-called dry cell. Okay, so first let's understand the different components of a dry cell. So this is something which you would have surely seen in your life. Okay, so you many of these batteries which you use, which are not rechargeable, have this particular configuration. It's the cylindrical battery, um, cylindrically shaped battery. So it has a graphite rod which acts as a um, electronic conductor. So it has a metal cap that is in contact with the graphite rod. Then there is an outer casing, all right? So um, so only this and this metal cap is connected to the graphite rod. There's an electronic contact. However, there is an insulator here. And then this graphite rod is in contact with the cathode mixture. So even though you say it's a dry cell, this might be a dry or it's a paste. Okay, so you don't have um, electrolyte sloshing around. However, an aqueous electrolyte might be mixed with a powder, which gives rise to a paste. So this cathode mixture is in contact with the graphite. Then there is a paper separator, which one of its primary role is to separate the cathode mixture from the anode. However, it may allow for the transfer of ions. So electrolyte, within the electrolyte, you need to have transport of ions. So the paper separator facilitates separation of the anode component from the cathode component, but allows for the transfer of particular some kind of an ion. And here the zinc case is there, and which in time, as the battery gets discharged, the zinc will get oxidized to zinc 2 plus. So just to emphasize the reactions, the negative electrode or the anode. Okay, in this case, it's unambiguous. So anode is where oxidation occurs. When you say negative electrode, it specifies, it gives you a pointer to the direction of the conventional current. And once you know the conventional current, the opposite, the direction of the electronic current is opposite to that of a conventional current. So this is the reaction that occurs at the anode or the negative electrode. At the cathode, you have this reaction. This is very much similar to what you saw in the previous slide, except that this is in this paste. Okay, so it's not an electrolyte that is sloshing around, but the paste has some amount of aqueous electrolyte in them. So the reactions are very similar, but you can carry it around. It can be transported much more easily because you don't have any electrolytes sloshing around. So this is a very common geometry which is widely still used, even though it was first demonstrated many, many decades ago. So the overall reaction is the following. So when you talk about half cell reaction, you can explicitly see electron transfer. When you look at the full cell reaction, you don't see any electrons in the reaction. So zinc gets oxidized to zinc 2 plus. This zinc 2 plus is that is a coordination compound formed between zinc 2 plus, ammonia, and chloride. So all this gives rise to this particular component. And MnO2 gets reduced to this particular component. So the overall reaction is the following. So this often called zinc carbon cell or zinc chloride cell. Okay, so and this is the geometry of the cell. So it still has certain disadvantages. So what are the disadvantages? So there are two specific disadvantages. One is there is gas evolution in this reaction. So zinc can react with this component. It will get oxidized to zinc 2 plus, but it will liberate ammonia, which is dissolved in the electrolyte. However, it gives rise to hydrogen gas. So if there is hydrogen gas, that will accumulate inside this container, and it will if there are a lot of hydrogen gas that is liberated, the battery might explode, or even if there's only small amount of gas, it may distort or change the geometry of the cylindrical battery. Okay, so this is a big disadvantage. And in addition, this particular component is mildly acidic. Okay, so typically when you have acidic substance, they give rise to corrosion. Okay, so you want to avoid very acidic media because many of the metals or metal oxides tend to get corroded in the presence of an acid. Okay, so even if it's a mild acid, even if you have pH 5 or so, you would the corrosion gets enhanced. So that's not very useful. Okay, so as you can see, this is as you can, there's no electron transfer. So there's no electron transfer in this particular reaction. Even though there's a charge transfer. So in this case, zinc gets oxidized. While that happens, this gets reduced to ammonia. So corrosion and gas evolution is the big disadvantage of this particular battery. So that was overcome with a very, very popular battery that is still produced in large quantities. This is the so-called alkaline batteries that I introduced in the second slide. So let's look at the geometry. Okay, so first, this is the geometry from the previous slide. It is what I mean by an inside out is that if I look at this, zinc was at the outermost layer or at the periphery of the battery, if not the outermost layer, it's at the periphery of the battery. However, in this case, zinc or brass, okay, so it's at the inner part of the battery. Okay, so this cylindrical component is the brass which acts as an anode. Okay, so here zinc, which was closer to the outer casing, acted as an anode. Here the anode is inside. So here there was cathode mix. So, however, the inside has is the anode mix. So this anode mix is in contact with the good electronic conductor. So here the electronic conductor was graphite. That is not so in this case. So you have an insulator that is very similar here, and you have a metal cap um, and the metal base. So this has not changed, but the component is different. Okay, so the outer cathode is made up of steel, which is corrosion resistant. So this also acts as a current collector. Okay, so this being a good electronic conductor that can act as a current collector. So typically when you say there's a current collector, that's a good electronic conductor. So the cathode mix is in contact with this steel cathodic current collector. And again, there is a separator as was a separator in this case. So what is advantage with respect to this particular chemistry? So the mildly acidic um, component was replaced by the less acidic zinc chloride. So when you have a less acidic medium, the corrosion is in general lesser. So this was one change. And so as you can see here, the aqueous component is is not acidic. Okay, so the corrosion problem has been overcome. And as was discussed in the previous slide, when there is no corrosion, the one of the product of the corrosion, which is evolution of hydrogen gas, is also not there. So both hydrogen gas evolution and corrosion were eliminated using this chemistry. This is a very, very widely popular and fairly inexpensive battery. So you might have also seen a battery in some other configuration as opposed to this cylindrical configuration. This is called a button cell. The chemistry is in a way similar. It also has a zinc electrode, which during discharge will get oxidized to zinc 2 plus. It has a separator and so on, and there's a cathode mixture. So the role of the cathode mixture is the cathode mixtures or the positive electrode, they are all oxidizers. Okay, so in the process of being an oxidizer, they themselves will get reduced. So you may have oxide of mercury, which is a solid. It as it provides oxygen for oxidation of zinc, it will get reduced to silver, mercury liquid. So here you have silver oxide. The oxide of silver gets reduced to silver metal. So in these are three possible oxidizers, three possible options for the positive electrode. Okay, so you may have a battery with this positive electrode or this positive electrode or this positive electrode. What is interesting about this is this oxidizer itself is a gas. This is O2 gas. So in a way, the battery should be permeable to gas. Okay, so these are like air breathing electrodes. Okay, so this is a very interesting kind of battery. So oxygen gas gets reduced to this particular component. So this is also a common class of batteries. So what is the recent development? When I say recent, you should understand that it's not these recent development were not that that's something that occurred in the last couple of years. Okay, in the time scale of technology development, it takes decades to replace a particular technology. Okay, so it may be 3 decades or so, but uh, the once because one of the main reason is that once the manufacturing and large scale production has been standardized, it is not very easy to replace that large scale technology. The associated risk is fairly significant unless the basic science or commercial utility has been well demonstrated, typically the replacement does not occur. Okay, so this theme you should be aware of when you try to propose a particular um, change in chemistry. You may put when you do research, for example, in a master's or a PhD, you may propose different chemistry. However, all these chemistries are um, it's not very easy to translate this research, fundamental research, to technology, because the challenges in commercialization and large scale manufacturing are very different. But one particular theme that has occurred over the last, let's say, 30 years or so, 30 more than 30, 40 years, is that replacement of the zinc component by lithium. Okay, so the negative electrode, instead of having zinc, lithium gets oxidized, um, and it has two particular advantage. First, lithium is a light metal compared to zinc or lead and so on. So these kinds of lithium-based batteries are very uh, useful for transportation application. For example, in case of electric vehicles, also for any mobile application like mobile phone or your laptop battery. Okay, so and the second advantage is the reduction potential of lithium is very negative compared to other options like zinc and so on. Therefore, all the lithium ion batteries have significantly higher cell potential. Okay, so the lead acid battery has this cell potential, but the lithium ion batteries almost the potential is twice as much. And compared to your most common NiCad battery or alkaline battery, the lithium batteries will have more than twice that potential. So that is a significant advantage. So these are in a way the class of lithium batteries are the latest large scale batteries that are being generated. The positive um, electrode uh, still has remained to a good extent. Manganese dioxide is still utilized. Okay, so the structure of this manganese dioxide is fairly complex. But it is still widely used oxidizer or a component of the positive electrode. So the reaction that occurs is that the lithium will react with MnO2 and an electron to form this particular solid. Okay. So, and so I would also like to mention a few other important class of batteries to give you an idea of certain advantages and disadvantages of battery chemistries. So uh, lithium thionyl chloride battery is also very common. What is unique about that is this this thionyl chloride. This acts as a component of the positive electrode, as well as it is a solvent for the supporting electrolyte. So we have discussed supporting electrolyte, the meaning of supporting, the role of supporting electrolytes in previous set of lectures when we looked at the transport in electrochemical systems. Um, so what is unique about this particular class of battery is that the oxidizer, lithium thionyl chloride, also acts as a solvent for the supporting electrolyte. So this is also a very common battery. Um, I mean, for specialized application. So all these things which I'm trying to show are have specialized applications. So for example, you may have a battery that is activated by seawater. Okay, so typically in this battery, you have anode and cathode, um, which are solids, and it gets activated only when seawater is being added to it. Okay, so why is this important? Because, for example, there are certain alarms, okay, which have to be activated in sea or in oceans, and the way to trigger the discharge of the battery is by addition of the seawater that acts as an electrolyte. The overall reaction for this specialized kind of battery is something like this. You may have other specialized batteries. These so-called reserve batteries have the same concept. These are also primary batteries. They're typically activated by bringing together some component. The component can be, in the previous case, in the previous slide, the electrolyte was brought together to activate and trigger the discharge of the battery, or the anode and cathode component can be brought together to initiate the discharge of the battery. Or you may also have thermal triggers. Okay, a change in temperature might change a particular property of the electrolyte. Maybe, let's say, it makes the electrolyte more conductive, and this may initiate the discharge of a battery. Okay, so why are these things important? Because when you may have to have a battery which is operational for 20 years, that is, you have it at a particular location, but they when you initiate the discharge might differ. So when you are not discharging the battery, you do not want the battery to self-discharge. Okay, so this is a particular phenomena. We will address this as we progress in this course. So you do not want self-discharge of the batteries. So these reserve batteries have very low self-discharge, and the side reactions are negligible, these batteries. Okay, so for those batteries which are operational for a long period of time, you may um, uh, generate very low power or very low current um, in these batteries, because the self discharge or the side reactions are negligible in these batteries. So um, and you may also have batteries for um, pacemakers. Okay, so these are batteries that are inside human body. So you do not want any liquid component. So the main um, advantage of these batteries is that all the components, okay, so the are solid. Okay, so the overall reaction is lithium reacts with iodine and forms this solid component. Okay, so this is again a class of specialized set of battery. This is the battery for pacemakers. So what few things I wanted to convey in this lecture. One is that what are some of the different classes of primary batteries um, was elucidated. The second aspect I want to convey is the variety of battery chemistry. There are actually thousands of uh, battery chemistry, because all you want is a component that gets oxidized and component that gets reduced. Okay, so in the beauty of chemistry is that there is an enormous variety in possibilities. So the battery chemistry can be very large. The set of battery chemistry possible can be very large. The other thing which I want you to notice is that despite the huge variety in battery chemistry, the number of commercial systems is much lesser. Okay, so you may come up with different battery chemistry to get it commercialized, and large scale utilization of batteries is altogether a different challenge. Okay, so this is something you need to be sensitive to, and the time scale for commercialization is also usually it's in the order of decades. It's not just a couple of years. So where do we go next? um, as I mentioned, secondary batteries are those which can be recharged. We will be discussing some of the common battery chemistries that go into secondary batteries. Thank you.